Hey everyone, and welcome to Cognito Key. Have you ever wondered how your computer can stream music, download a huge file, and let you type in a document all at the same time? Well, it's not magic. It's all thanks to a really clever concept called multithreading. And in this explainer, we're going to pull back the curtain and see exactly how it all works.
So here's what we've got lined up. First, we'll look at why just doing one thing at a time is a recipe for disaster in modern computing. Then we'll jump into multithreading as the solution. We'll meet the two types of threads that are the stars of the show, and then we'll dive deep into the three main ways they connect with each other. And finally, we'll find out which model is actually powering the devices you and I use every day.
All right, so to really appreciate the solution, we've got to understand the problem first. Imagine a traditional computer process is like a car on a really narrow one-way street. It can only move forward, and it can only do one thing at a time. This is basically the world of single-threading.
I'm sure we've all been there, right? You click Save on a really big file, and suddenly, the entire application just locks up. You can't type, you can't click on any menus, it's totally frozen. Well, that annoying experience is often the direct result of a single-threaded design.
You see, a traditional process has just one single thread of control. Think of it like a workshop with only one worker. Now, if that worker gets busy or stuck waiting for something, like say saving that giant file, the whole entire workshop just grinds to a halt. Nothing else can get done until that one task is finished. It's just super inefficient.
So, how do we fix this bottleneck? Well, it's simple. We add more workers, or in this case, more threads. And that is the whole idea behind multithreading, turning that narrow one-way street into a massive multi-lane highway.
And the difference is just night and day. A single-threaded process gets completely stuck if one task gets a snag. Everything just stops. But with multithreading, other tasks can just keep on running like nothing happened. And all of a sudden, we're making way better use of our computer's power.
A modern word processor is actually a perfect example of this. You've got one thread that's just handling your typing, so the cursor moves the instant you press a key. At the very same time, another thread is busy checking your spelling in the background. A third one might be displaying images, and a fourth could be auto-saving your work every few minutes. All these little workers are cooperating to give you that smooth, seamless experience.
Now, to get how this all works under the hood, we need to meet the two main players in this game, user threads and kernel threads. You can think of them as the two different types of workers we have to get the job done.
Okay, so user threads are managed by the application itself in what we call user space. This makes them incredibly fast and lightweight to create and manage. In fact, the operating system's kernel doesn't even know they exist. Kernel threads, on the other hand, are managed directly by the OS. The kernel is aware of every single one, but that level of control comes with a price. They're a bit slower and take up more resources to create.
So we have these really fast application-level threads, and then we have these powerful OS-level threads. The real million-dollar question is, how do they work together? Well, operating systems use three main strategies, or models, to map one to the other. The first approach is called the many-to-one model. And just like the name says, it maps lots of user-level threads that your application creates to just a single kernel thread that the operating system can see. Now, the upside here is speed. It's a very efficient way to manage threads. But the downside is a huge deal breaker. If just one of those user threads has to wait on the system for something, like reading a file from the disk, the entire process freezes. We're right back to that same frustrating problem we started with.
Next up, we have the one-to-one model. This approach is much more straightforward. It gives one dedicated kernel thread for every single user thread that the application creates.
The benefit here is massive. You get what's called true concurrency. This means multiple threads can actually run on different processor cores at the exact same time. If one thread has to wait, it doesn't affect the others at all. The catch, though, is overhead. Creating a kernel thread for every single user thread is pretty resource-heavy, and the OS might even limit how many you can create.
And this brings us to our third and most flexible option, the many-to-many model. This model is like a compromise, mapping many user-level threads to a smaller or maybe equal number of kernel threads.
This model really tries to give us the best of both worlds. Developers can create as many lightweight user threads as they want, and if one of them has to wait, the kernel can just grab another ready thread and schedule it to run on an available kernel thread. So this avoids the total freeze of the many-to-one model and the heavy overhead of the one-to-one model.
Okay, so we've got these 3 different models, and each has its own set of pros and cons. Let's wrap things up by taking a look at which of these approaches actually got used in the real world.
Just take a second to think about it. With everything we've talked about, which model do you think powers the operating system you're using right now? The simple one, the powerful one, or the flexible hybrid?
Well, while some early systems played around with the many-to-one and many-to-many models, today's heavyweights like Linux and Windows have pretty much all settled on the one-to-one model. So why is that? It's because our computers have gotten so much more powerful, with multiple cores. That overhead we talked about just isn't as big a deal anymore. The guarantee of true, unblocked performance is just too good to pass up.
So let's do a quick recap. Multithreading is how modern computers can get so much done at once. We saw the simple but flawed many-to-one model, the powerful but expensive one-to-one model, and the flexible many-to-many hybrid. Each one is just a different trade-off between speed, power, and complexity.
So the next time your computer is juggling 10 different things without even breaking a sweat, you'll know what's going on. It's this incredible, constant balancing act happening behind the scenes, all to give you that smooth, modern computing experience we all take for granted.
If you found this explainer helpful, do me a favor and hit that like button. And make sure you subscribe to Cognito Key for more deep dives into the tech that shapes our world. Thanks so much for watching.